The classification of the signal is even and odd. So again, as I said, we have two types of signals. Let's say continuous time signal and discrete time signal. Now the definition goes as follows: a continuous time signal x of t is an even signal if and only if x of t is equal to x of minus t, or sometimes the proper way of writing this is x of minus t is equal to x of t, instead of writing like this. While a discrete time signal is even if and only if x of minus n is equal to x of n. So this is the condition for evenness, and this should hold for all values of t, and this should hold for all values of n. So this is the condition for evenness. Okay. Now similarly, a continuous time signal x of t is odd if and only if x of minus t is equal to minus of x of t. Sometimes people will write x of t is equal to minus of x of minus t, or you can write like this. Similarly, a discrete time signal x of n is odd if x of minus n is equal to x of n for all values of n, and this also for all values of t. An important note here is an odd signal must necessarily be 0 at t equal to 0. So okay, because we said odd signal, the condition is x of t is equal to minus of x of minus t. When t equal to 0, then you will get x of 0 should be equal to minus x of 0, because let me put minus here. Minus 0 I can write as x of 0. Now x of 0 should be equal to x of minus 0. When will this condition occur, or when will this condition happen? When only 0. When x of 0 equal to 0, then I can write plus 0 or minus 0, not a problem. I cannot say plus 1 is equal to minus 1. No, this is not possible. Similarly, for a discrete case, x of 0 must be equal to minus x of 0 only when x of 0 is equal to 0. So remember this. Okay. Now even signals are symmetrical about the vertical axis, say t equal to 0, or the time origin. So t equal to 0 is also called time origin. So if we have a function like this, it is symmetrical. So my picture is not very good, but assume that this is symmetrical. Left hand side is symmetrical with respect to the right hand side. Whereas odd signals are anti-symmetric about the time origin. So this is even for odd signals. Let's say like this. Probably when t equal to minus 1, you have minus 1. When t equal to plus 1, let's say plus 1. So this is an example of odd signal. Now the next point is, you take any signal x of t. This x of t can be decomposed or broken into a sum of two signals. Okay, any signal you can break into two signals. So what are those two signals? One is an even part of x of t and plus the other one is odd part of x of t. So any signal x of t can be written like this. Okay, so you can find out also. So let me denote the even part of x of t by x suffix e of t and the odd part of x of t by x suffix o of t. So therefore x of t can be written like this. The same thing goes for discrete case also. This is continuous time signal. For the discrete case, x of n is equal to x odd of n, odd part of x of n. Sorry, first even part. You can even write odd part also in the first, no problem. It's not an issue. Plus x odd part of n. Now from this equation you can find out what is even part and what is odd part. Let's say this is 2 and this is for discrete time signal. Parallelly I will discuss even part as well as odd part. Now how do you find out x even part of t and x odd part of t? Let's say this is equation 1. From equation 1 replace t by minus t. So what will happen? X of minus t is equal to x even part of minus t plus x odd part of minus t. Now we said a signal is even if x of minus t is equal to x of t. So since it is even, I can write as x e of t. And this is odd. If it is odd, then I can write x o of minus t is equal to minus of x o of t. Therefore this is my x of minus t. Let me call this is equation number 3. Okay, now add 1 and 2. If you add 1 and 2, then the left hand side you have x of t plus x of minus t. The right hand side you have 2 times of x even of t plus 0, this part and this part will get cancels. This part and this part will get cancelled. So finally you will end up with this equation. Okay, so this implies x even part of t, even part of x of t is equal to x of t plus x of minus t divided by 2. Therefore whenever you want to find out the even part of x of t, what you do? You take x of t, then take the time reversal of x of t, that is x of minus t, add these two guys and divide by 2. That will give you the even part of x of t. By the same token you can do 1 minus 2. So sorry, 1 minus 3. What I did, this is not 2, I am sorry, this is not 2, this is 3, I am very sorry, 3. Now similarly you can do 1 minus 3. Where is 1? 1 is there. So 1 is here and 3 is here. 1 minus 3. So 1 minus 3 x of t minus x of minus t is equal to, anyway this x of x e of t and this x e of t will get cancelled, and this x of t, x o of t and this x o of t becomes plus, so 2 times x o of t. So this implies x o of t, odd part of x of t, is equal to x of t minus x of minus t divided by 2. So this is the odd part of the signal x of t. So we got the two results now. So the even part of x of t is equal to x of t plus x of minus t by 2, and the odd part of x of t is equal to x of t minus x of minus t whole divided by 2. The counterpart for discrete time signal is x suffix e of n is equal to x of n plus x of minus n whole divided by 2, and the odd part of x of n is x of n minus x of minus n divided by 2. Okay, and this odd part of x of n is denoted by OD, capital O d of x of n. Similarly, this is denoted by even part of x of n, and this one is denoted by odd part of x of t, and this one is even part of x of t, like this. So that's all about even signal and odd signal. And some more points I would like to introduce for complex valued signal. These all are real signals, like we assumed x of t is real, and x of n also real signal. Till now we assumed both are real. Now one can ask the question, if x of t or x of n is complex valued signal, then what will happen? That time we will not talk in terms of even signal or odd signal. We will talk, or we will name it as conjugate symmetric and conjugate anti-symmetric sequences, or conjugate symmetric signal and conjugate anti-symmetric signal. So let us take this conjugate symmetric and conjugate anti-symmetric. This is defined only for complex valued signal. Even you can define real signals also, but it does not make much sense. Okay, you take a sequence x of n, and this sequence is called a conjugate symmetric if x of n will be equal to x conjugate of minus n. Okay, if it is a real valued sequence, then it is called a even sequence, like what we did previously. If x of n is real, then this condition is called even symmetric. Okay, if x of n is complex valued sequence, then this condition, let me call 1 is called conjugate symmetric sequence. Okay, now let us talk about conjugate anti-symmetric sequence. A sequence x of n is called a conjugate anti-symmetric sequence if x of n is equal to minus of x conjugate of minus n. Okay, so this condition is needed for a sequence to be an anti-symmetric conjugate sequence. So a real conjugate anti-symmetric sequence is called an odd sequence. As I said, if x of n happens to be real, then it becomes an odd sequence. Simply you can call odd sequence. On the other hand, if x of n happens to be a complex valued sequence, then this is called a conjugate anti-symmetric sequence. Okay. As I said, for conjugate anti-symmetric, as I said, for odd symmetry, like x of 0 should be equal to minus x of 0. This happens only when x of 0 must be 0. This is a condition for real valued sequence. If it is complex valued, then how does this condition will change? For complex valued sequences, then x of 0 must be equal to minus x conjugate of minus, anyway minus 0 is again plus 0, let me put like this. Now when does this condition will be true? Like you have a sequence like this, let us say this value is 2j height is, and this is 3j 3 plus 2j, and this one is 1 plus 2j, like that. This is 0 1 like that. So if you take conjugate of this sequence, then what will happen? One second, I am slightly messing up here and there. Now the question is, when does this condition will be true? Let us say at this point we have only purely imaginary value, let us say 3j, and this one is 3 plus 3j, and here I am having 3 minus 3j. Sorry. Now this point is 0, this point is 1, 2, minus 1, minus 2, and this is time axis, and this is, let us say, x of n. Now what is x conjugate in this case? X conjugate of n, take the conjugate of that. So this becomes minus 3j, because real part is 0, here real part is 0. And what about this guy at 1? This becomes 3 minus 3j. And what about this point? This point becomes 3 plus, let us say, I am cooking up an example, so that is why I am doing corrections here and there. 3 plus 3j. So therefore 3 minus 3j. Okay. Now this is x conjugate of n. Now what is the time reversal of this conjugated sequence? Just inverses. Okay, so this becomes 3 minus 3j, and this becomes 3 minus 3j, and this will be minus 3j. Now what is the condition? What is our original signal? The original signal is here. 3 plus 3j, 3 minus 3j, you put a minus here. Okay, and this is plus 3j. This is 1, 0, minus 1, the n goes. This is x of n, that is x conjugate of n. Now x of n should be equal to minus of x conjugate of minus n. You substitute n equal to 0, then in this case you will get plus 3j, and in this case you will get x conjugate of minus n is this one, minus 3j. Again if you take minus of that, then it will become 3j. Therefore, at n equal to 0 at the origin, you should have purely imaginary value, otherwise this conjugate anti-symmetric sequence property will not hold. Okay, that is what I want trying to say here. Now, rest of things you can compare. I do not know how this both will match. Let us say this is x conjugate of minus n, then you can compare one by one. Substitute n equal to 1, then x of 1 is this one, and x conjugate of minus 1 is this one. So, minus of minus it will become plus, so they are equal. Okay. So, that is a point I would like to say here. Consequently, for real odd sequence, x of 0 should be 0. If it is real, then x of 0 must be 0. If it is a complex valued sequence, then x of 0 must be purely real valued sequence. Real valued sequence. So, any complex sequence x of n can be expressed as a sum of its conjugate symmetric part and its conjugate anti-symmetric part. I wanted to make sure that this example is correct. Okay, from this it is correct, x conjugate of n, and this also correct, but are they equal? Let us say figure 1 and figure 2. It may not be conjugate anti-symmetric, you can check it out. For all values of n, x of n should be equal to minus x conjugate of minus n. You can verify this. Substitute n equal to 1. Yes, n equal to 1, it satisfies. X of n equal to 3j. The right hand side minus of x conjugate of n is minus 3j. So, 3j equal to 3j. Okay, it is satisfying at n equal to 1. Then when n is equal to 2, n equal to 0 this is. When n is equal to 1, x of 1 must be equal to minus of x conjugate of minus 1. What is x of 1? 3 plus 3j. What is x conjugate of minus 1? 3 minus 3j. Multiply by minus 1. So, it becomes minus 3 plus 3j. The left hand side it is 3 plus 3j. So, they are not equal. Therefore, this sequence is not conjugate anti-symmetric. They are not equal for n equal to 1. Therefore, you cannot say that they are conjugate anti-symmetric. You can cook up an example, okay, like this. That's I wanted to make sure whether it is conjugate symmetric or a conjugate anti-symmetric sequence. So, as I said, for a real signal x of t, it can be written as even part of x of t plus odd part of x of t. Similarly, for complex valued sequence, x of n can be written as conjugate symmetric Cs of n plus conjugate anti-symmetric Ca of n. Sometimes people use small c and small s and small c and small a suffix. This is for complex valued sequence. Okay. Now, similarly, you can find out what is the conjugate symmetric part of x of n and this is small a. Let us say small c, small is conjugate symmetric, and this is small c, small a, conjugate antisymmetric. Now conjugate symmetric part of x of n is equal to x of n plus x conjugate of minus n whole divided by 2. Similarly, x conjugate antisymmetric sequence is obtained by CA of n is equal to x of n minus x conjugate of minus n whole divided by 2. So this one you can write as even part of the signal n, and this is odd part of x of n. See, the computation of the conjugate symmetric and conjugate antisymmetric parts of a sequence involves conjugation first, then time reversal and addition, okay, and then multiplication. Multiplication is here 1 by 2. 1 by 2 is treated as multiplication of 0.5. Okay, so first step is you have to conjugate the sequence. If you do conjugate, then what happens? X of n becomes x conjugate of n. What is the second step? Time reversal. So time reversal means x conjugate of n becomes x conjugate of minus n. Then what is the third step? Addition. Okay, like x of n plus x conjugate of minus n, and or you can x of n again here, this also addition, but you observe the minus inside. Okay, so x conjugate of minus n, that is the third step, and the fourth step is multiplication. Actually it is a division, but division is performed in terms of multiplication. So 1 by 2 is equal to 0.5, right? So instead of dividing by 2, you multiply by 0.5. So therefore 0.5 times x of n plus x conjugate of minus n. Okay, or 0.5 times x of n plus, you observe the minus inside, x conjugate of minus n, like this. So these are the 4 steps that involves to find out the conjugate symmetry part of a sequence x of n, complex valued sequence x of n, and the conjugate antisymmetric part of a complex valued sequence x of n. So because of the time reversal operation, the decomposition of a finite length sequence into sum of a conjugate symmetric sequence and a conjugate antisymmetric sequence is possible. Okay, so the length should be finite. If the length is infinite, then we cannot do it. Okay, so if the parent sequence, that is original sequence, is of odd length defined for a symmetric interval, that is minus m less than or equal to 0 less than or equal to m. So in this case you can define this conjugate symmetric sequence and conjugate antisymmetric sequences. Therefore in general, x of t is the sum of even part of x of t plus odd part of x of t. Let us take one example. Let me take a discrete valued sequence so that it will be very easy for me to work on it. So my sequence is like this. At 0, it has a constant value of 1, and let us say this is 1, 2 and 3. At 1 the signal strength is 1, at 2 the signal strength is 0, and at 3 the signal strength is at 1 it is 1, at 2 it is 1, at 3 it is 1, all are 1 volts. Okay, so this is like equally distributed, and beyond that no value for me. And here at -1 the signal strength is 0, and here also -2 again 0, and -3 it is 0, and beyond this the points are undefined, not defined. Okay, and here also the points are at 4, 5, 6, they are not defined. I mean, you cannot say it is 0, but it is not there, that's all. So you have the range is from -3 to +3, that's all, nothing more else. Okay, so no, 1 second, no, it has a value, like it keep on goes in the right hand side, but in the left hand side, I am sorry, it is defined. I am sorry, I did not take the example properly. It is infinite sequence, infinite length sequence. Let us assume it is defined, it is let us take infinite sequence length. So it keep on goes up to infinity, the value is 1. In the left hand side all are zeros. So how do you describe mathematically this sequence? X of n is equal to 1 when n is greater than or equal to 0, and 0 when n is less than 0. Okay. Now you can find out even part of x of n. How do you find out? That is going to be x of n plus x of minus n whole divided by 2. X of n is given, you need to find out x of minus n, just reverse. Okay, flip over, flip the sequence about n equal to 0. This point is n equal to 0. Then what happens? You will get 0 at n equal to 0, you will get 1, n equal to minus 0, you will get 1, n equal to minus 2, you will get 1, and so on, it keep on goes up to minus infinity. But what about this side? 1 at 2, 0 at 3, 0. So this all are zeros in the right hand side. So this is my x of minus n. Now add this signal and this signal, or else I will neatly draw now. 1 second. This is very crucial point. Maybe originally your sequence is like this: 1, 1, 1. So it goes like this. Okay, and here 0, 0, 0, like this it goes in the left hand side. So how do you define this x of n? X of n is equal to 1 when n is greater than or equal to 0, and 0 when n is less than 0. That's it. This is your x of n, and all are with the amplitude of 1. Now how do you define x of minus n? By the way, this is a real sequence. You just flip over around n equal to 0. This is 0, 1, 2, minus 1, minus 2, minus 3. Similarly 0, 1, 2, minus 1, minus 2, minus 3. Now whatever the value you have at 1, that will come to minus 1. And whatever the value you have at 2, n equals 2, that comes to n is equal to minus 2. Like this it keep on goes. Therefore this one is coming here, and this one is coming over here, and if you have one more one here, and that comes here. So just you are flipping at about the time t equal to 0. Okay, vertically you are flipping over. So this is the time axis, and this also time axis. Right. Now what do we need? You add x of n plus x of minus n, term by term you add it. Okay. If you add, what will happen? Now after addition you multiply by 0.5, that is by 2. So at n equal to 0, the signal strength is 1 here and here also 1. Therefore, 1 plus 1 2, 2 by 1 again 1. Now, at n equal to 1 here is 0 and here it is 1. So, 0 plus 1 it becomes half, right. Now, at n equals 2 you have 0, at n equals 2 you have 1. So, 1 plus 0 becomes 1, divided by 2 it becomes 0.5. So, at n equals 2 it becomes again 0.5. So, this is 1, this is 2, this is 0. So, like that it keep on goes 0.5, at 3, 0.5, at 4, at 0.5, it goes up to infinity. So, all the values are infinity, right, starting right from n equals 1. Similarly, for the left hand side, if you look at, here the value is 0 and here the value is 1, 1 plus 0, 1, divided by 2, 0.5. Therefore, at n equals minus 1, it becomes 0.5. And here the value is 0 and here the value is 1, 1 plus 0, 1, divided by 2, 0.5. So, at n equals minus 2, the value is 0.5. Similarly, at n equals minus 3, the value is 0.5. So, this is the typical, so this is the even part of x of n. What is this? Even part of x of n. By the same way, you can find out the odd part of x of n. Before that, how do you describe this mathematically? The even part of x of n is equal to, it is 1 when n is equal to 0, it is half when n is, it is half when n is less than 0 and it is half when n is greater than 0. Okay. Now, by the same way, if you add, if you subtract this one from that, from x of n, then you will have the sequence like this. At n equal to 0, you have 0 value and then it is plus half, plus half, plus half, and here it will be minus 0.5, minus 0.5, like that it goes 1, 2, 3, minus 1, minus 2, minus 3. It goes up to minus infinity and this goes up to plus infinity, and this signal is odd part of x of n, x o of n. Now, look at the origin the value is 0, otherwise you cannot claim that the signal is an add signal. By looking at the signal itself, you can say whether the signal is an odd signal or an even signal. Okay, no need to do this thing or no need to do the testing and all. Just simply looking at the sequence, you will come to know whether the sequence is an odd symmetry or even symmetry. The very first step is you should find out, but that is not sufficient condition. The necessary condition should be, it should be equal to 0 at n equal to 0. And after that you have to check again one more. Okay, if somebody comes and says, okay, my sequence is 0 at n equal to 0, then you cannot say the signal is an odd signal. Again you have to go for the further testing. But the first condition, if n equal to 0, it is non-zero, then you can comfortably say that that signal is an odd signal. Now, how do you write mathematically this one? X odd of n is equal to minus 0.5 when n is less than 0 and it is 0 when n is equal to 0 and plus 0.5 when n is greater than 0. So, this is an example of the even and odd decomposition of a discrete time signal. Similarly, you can do this for continuous time signal also, but I have taken discrete time signal because it is very easy to work on it. So, let me stop at this point. In the next lecture, we will talk about exponential signals and sinusoidal signals. Thank you very much.